All right, so this is the final video showing you how to calculate or to help you figure out how to calculate the total number of lysine and arginine residues in BSA. However, again, I'm not going to go through a sample calculation with you for those specific conditions because then everyone's just going to get the correct answer. I will give you kind of like a peripheral example, and hopefully you can take what you learn from this and adapt it to what your to the data that you obtained for that specific prompt in the post-lab write-up, which is prompt C5. All right, so this question here, the enzyme that I'm using, it's not going to be trypsin, it's going to be chymotrypsin. It's going to change the conditions just a little bit. Chymotrypsin. This one does not have a optimal pH at 8.5. This now has an optimal pH of 8.0, and that's something that we're going to have to take into account for our calculation. Trypsin, on the other hand, the enzyme that you use in your experiment, has an optimal pH of 8.5. That's why we set our experiments at 8.5, so that we can get it going as fast as possible. But for this example, the pH that we are trying to, the starting pH was 8.0, and we kept it at 8.0 for the duration of the experiment. Trypsin recognizes phenylalanine, tyrosine, and also tryptophan residues. So the number that I'm going to calculate in this one is going to be the number of phenylalanine, tryptophan, and tyrosine residues per this protein. And I'm just going to use like a generic protein here. I'll just call it like protein A. And in the experiment, I ended up using 150 milligrams of this protein. The amount of BSA that you used in your experiment obviously is going to be different. And for this protein, I'm just making up a generic formula weight for it, or a relative mass. That is 50,000 grams per mole. All right, and then what else do we need from this? Okay, so the entire pH, the pH of the experiment for this pH-stat experiment was pH 8.5. And then in the end of the experiment, I had added a total of 10 mils of 0.01 normal potassium phosphate. That's going to be the only thing that will be the same as the 0.01 normal potassium phosphate. And this is it. This is all the data that I need to go move forward and figure out for this specific protein A, how many total, or I should say, what's the sum of phenylalanine, tyrosine, and tryptophan residues in this protein. So the first thing that we need to do is revisit the Henderson-Hasselbalch equation to figure out what's the ratio of the titratable amino groups for every single peptide that's formed versus the untitratable amino groups, because we need to know the sum of these two groups in order to back calculate correctly. So the Henderson-Hasselbalch equation again says that pH of the solution is equal to the pK of the functional group you're looking at plus the log of the conjugate base species concentration over the concentration of the acid species for that functional group. And here we're talking about, the amino groups that are newly formed every time the peptide has been cleaved or the protein has been cleaved. The conjugate base being the NH2 group, and then the acidic species is the NH3 plus group that we're looking at, just so everyone knows what we're referring to. So the pH of the solution was the starting pH of the experiment, and also the pH that we kept it constant at. So that pH is going to be 8.0. And the pKa needs to be the pKa of the N-terminal amino group, which is not the same as the pKa of the amino groups off of, amino acids. This is going to be much more stabilized. Its pKa is going to be a lot lower. That pKa is 8.2. It's also in the book. It's the same pKa that you'll use for your post-lab write-up as well. And then the log of the concentration of the conjugate base over the concentration of the acid species. When we subtract both sides by 8.2, we get negative 0.2 on the left side equals to the log again of the conjugate base concentration over the concentration of the acid species. And then setting both sides of the equation to base 10, we end up getting 10 to the negative 0.2 equals base 10 of log base 10. Basically just gives you whatever was in the parentheses, which was the concentration of the conjugate base divided by the concentration of the acid. Now 10 to the negative 2 I have written here is 0.631. And I'm going to put it slightly higher because I'm going to add a 1 to the bottom of that. It's the same thing, except now I just have 1 in the denominator. And all I need to do now is just erase most of this other stuff that I don't need at this point anymore. And this is kind of like a weird ratio to have things in like a fraction of a decimal. So what I'm going to do is, and you can do this with any number you have, you're working with. I'm going to multiply the numerator and the denominator of this part of the equation both by 1,000. So this ratio now becomes 631 divided by 1,000. It's the same number as we got before. Now that, we have it in this nice ratio that makes a little bit more sense. And what this is telling us is that for every 1,631 peptide, newly formed peptide, or not newly formed, I should say newly cleaved peptide bonds, for every 1,631 newly cleaved peptide bonds, according to this ratio, 631 of them will be in the conjugate base form, meaning they're titratable because their proton was in the solution. And we titrated those with the potassium hydroxide up there. And then the other 1,000 are going to be in the acid form, not titratable. Now we can kind of erase our work down here. So what this is telling us is that in order to take into account all 1,631, or I should say, to take into account all of the newly formed, I keep on saying newly formed, of the newly cleaved peptide bonds, we need to set up this 1,631 divided by 631 correction factor. That is simply going to be the sum of the ratios in the numerator and then the conjugate base number of the ratio in the denominator. And that's how we set up our correction factor. That's why in the discussion slides where we went over that problem, our correction factor there was 3/2. Here in this problem, my correction factor is 1631 over 631. All right, now that we have that correction factor, we can also start removing some of this thing that we have here, some of these to make space. All right, so this is our correction factor. I'm just going to write it right here so I don't forget. And what we need to do is now figure out how many millimoles of peptide bonds did we make. Well, we can figure out how many millimoles of the titrant we added, and then we know the correction factor to account for all the millimoles of the peptide bonds. So we'll go ahead and do that. So 10 mils of the final amount of the titrant that we added. Again, 0. Oh, let me change the color on this so we can keep track of where everything is coming from. 0.01 normal of the titrant for potassium hydroxide is the same as 0.01 millimoles per milliliter. And that times 10 milliliters is going to give us a total amount of titrant that we added to the experiment being 0.1 millimoles. But that was the amount of titrant that we added to neutralize the protons from those titratable peptide bonds. We need to add that or account for that correction factor. And then the answer that we end up getting when we take 0.1 millimoles of peptide bond cleavages times the 1631 over 631 correction factor, we end up getting 0.258 millimoles of peptide cleavages. Oh, that's not the way you spell peptide at all. That's peptide. Peptide cleavages. So we have half of the work already done. We just basically need to then solve for the other part of the work, which is the value that goes in the denominator, which is the total millimoles of the protein that were in the experiment. So then what I'm going to do is, again, erase most of this stuff to get a little bit more space. How many millimoles of protein did we have? So if I put in 150 milligrams of total protein A, and the relative mass of that is 50,000 grams per mole, then I can take 150 milligrams and set up this conversion ladder where milligrams is going to be on the bottom, or sorry, well, 50,000 grams per mole is the same as 50,000 milligrams per millimole. Therefore, I'm going to put 50,000, that is hideous, 50,000 milligrams in the denominator in this conversion ladder and 1 millimole in the numerator. Milligrams cancel out. I'm left with millimoles as my answer. And then 150 divided by 50,000 is going to get me 0.003 millimoles of protein A. So that's it. I have these two values now. One is going to go in the denominator, one is going to go in the numerator. I'll keep on doing that. And I can now solve, should have wrote this out somewhere else, for how many of these phenylalanine, tyrosine, and tryptophan amino acid residues there are for protein A. So I will take the millimoles of the peptide cleavages, which equals the sum, the millimoles of the amino acids, 0.258 millimoles of phenylalanine, tyrosine, tryptophan, divide by, and then the millimoles of protein A, and what we end up getting are millimoles in the numerator and millimoles in the denominator cancel out. I'm going to erase this a little bit. And when we take 0.258 and divide it by 0.003, the number we obtain so nicely that I had calculated ends up being 86 total phenylalanine, tyrosine, and tryptophans per protein A. And if I knew the sequence of protein A, I would go ahead and count those numbers of phenylalanine, tyrosine, and tryptophan, making sure that I don't take into account any of them that are followed by a proline, because chymotrypsin also has some exception as well, just like its related enzyme trypsin. I actually don't even know if they're related or not. But trypsin itself also does not cleave lysine and arginine residues when followed by a proline. And hopefully you all understand that you should not be reporting to us your final answers as decimals, because there's no such thing as fractional amino acids. But yeah, hopefully this tutorial shows you how to do all of that work for calculating the number of lysine and arginine residues per molecule of BSA protein.